Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry Chapter 14.2 on the gas laws, and this is video part 3. So today we're going to be talking about the combined gas law. So we put Boyle's law and Charles's law together to get PV over T equals a constant, so we know P1V1 over T1 is going to have to equal P2V2 over T2. So let's tackle this. At sea level, 1 atmosphere and 20 degrees Celsius, the high altitude research balloon needs 18 cubic meters of helium to fill it. What is the volume of the balloon at an altitude of 100,000 feet with 0.01 atm and it is 50 degrees Celsius? All right, so please write the equation and I will meet you at the board. Okay, let's tackle this. At sea level, so that's where we're starting. So it is the temperature, T1, and the pressure, 1 atm, P1. The high altitude research balloon needs 18 cubic meters. So that is my volume, V1, of helium to fill it. What is the volume? So I'm solving for V2 of the balloon at an altitude of 100,000 feet, which is negative 50 degrees Celsius. That is my T2, and 0.0100 atm. That will be my P2. Alright, so I have my V1 equals 18 cubic meters. My V2 is my question mark. Let's do volume first. Pressure, excuse me. Let's do P1 equals 1.00 atm and P2 equals 0.0100 atm, and then our T1 is equal to 20 degrees Celsius. We have to convert it to Kelvin by adding 273 Kelvin, K, which would equal 293 K, and then my T2 is equal to negative 50 degrees Celsius, converting that into Kelvin. I really just want to write that K. $223 Kelvin is my answer. Whew. It's a little bit rough right here. Okay, negative 50 degrees Celsius, adding our conversion, plus 273 Kelvin equals 223 Kelvin is T2. Next thing we do is we write our equation. So we have P1V1 over T1. P1V1 over T1 is equal to P2V2 over T2. We sub in what we know. Pressure 1 is 1.0 atm, and pressure 2, let's just do this all at once, times 18 cubic meters over our T1, which is 293 Kelvin. So then our P2 equals 0.0100 atm times our V2, which is our variable, divided by our T2, which is 223 Kelvin. Alright, so what we should do is grab out our calculator and simplify the left side. and the right side, and then we will solve for the variable. So go ahead and take out your calculator and simplify the left side first. Okay, did you get 0.0614, and that's ATM times cubic meters over Kelvin? And then on the right side, did you get 4.484 times 10 to the negative fifth ATM over Kelvin times your V2. So we're going to take that number and divide it on each side. I don't want to write out all the zeros. I'll just do it in scientific notation. 4.484 times 10 to the negative fifth ATM per Kelvin, and divide that by 4.484. Times 10 to the negative fifth ATM per Kelvin. Alright, so we'll simplify things first, and so we know on this right side we're left with V2. On the left side, let's look at our units first. So ATM, ATM, those are going to cancel, and then Kelvin's on the bottom of a fraction, so it's like it's on the top, so those are going to cancel, and we're left with meters cubed. So then we're going to take 0.0614 divided by 4.484 times 10 to the negative fifth. Make sure to use your calculator correctly. Okay, did you get 1,369.96? And how many sig figs do we get? 2. That's 3. 2. So let's go with 2. We're not going to do the temperatures. We'll go with the pressure and the volume, which is 3 and 2. So we get, well, let's just go to 3, just for fun today. So technically 2, but we're going to go to 3. 1,370 cubic meters equals our final volume. Let's make that pretty, like keep volume as green. Equals our final volume. Okay, let's double check that that sounds correct. Coming up here, what is the volume? Yeah, we answered the question. So now at sea level, it is the pressure is higher, and so then as we go up, the pressure is less, so the volume has to be bigger. So then we know the volume should be bigger than this 18 cubic meters. And then when we have a temperature change, if the temperature goes down, then the volume also goes down, but which one affects it more? So let's think about that for a minute. Okay, so when we look at these, one of them should make it bigger, one of them should make it smaller. How do we know which one's correct? Well, let's look at our pressure. Now let's look at our temperature first. The temperature goes from 293 to 223. And then the pressure goes from 1 to 100th. So there's only 100th of the original pressure. So that's going to be a bigger factor. So if it was just pressure, it would be 100 times bigger. So it would be 1,800 cubic meters. But the temperature went down, so it's going to be a little smaller than that because the temperature, when the temperature goes down, the volume goes down a little bit. Okay, so is our answer bigger than the original one? Yes. And is it less than 1,800? It is. So good job. Okay, that was the combined gas law where we combined Boyle's law and Charles's law. And now we can't forget Avogadro. He did a lot of studying with gases and moles. So Avogadro's law, volume versus moles. So the volume and moles are directly related. So if you keep pressure constant, if you increase the number of particles, you have to increase the volume. So that makes sense. You have more particles, it's going to take up more volume. So then you may want to write down the other relationships in that scenario. So if you decrease the number of moles, you have to decrease the volume, particularly, or if the pressure is constant. And then if you increase the volume to have the same pressure, you would need more moles. And if you decrease the volume to keep a constant pressure, you would need fewer moles. So this is also really important with pressure. So moles and pressure are also directly related. If you increase the number of particles, you are going to increase the pressure if you keep the volume constant. So if we have a constant volume, when we increase the number of particles, number of moles, we're going to have more collisions on the side of the container, so we're going to have a higher pressure. So the other relationships, make sure you can figure these out or you write them down. If you decrease the number of moles, keeping the volume constant, you'll decrease the pressure. Also, if you increase the pressure and don't change the volume, you would have to increase the number of moles to keep that same volume. And then if you decrease the pressure, you would have to have fewer moles if you were to keep that same volume. So looking at the volume and the number of moles is a constant, which means our initial volume divided by our initial number of moles has to equal our second volume divided by a number of moles. So what does this mean? So if you have equal volumes of gas, they contain equal numbers of molecules regardless of which gas they are. So one volume is going to have the same number of moles as the same volume of a different type of gas. So if I have 2 moles of hydrogen and 1 mole of oxygen gas and 2 moles of water vapor, the 2 moles of hydrogen gas are going to take up the same volume as 2 moles of water vapor. So like I said, we've been talking about 2 moles of hydrogen gas react with 1 mole of oxygen gas to form 2 moles of water vapor. But we could also say a volume, because we know moles and volume are the same when we're talking about gas. So 2 liters of hydrogen react with 1 liter of oxygen to form 2 liters of water vapor. So the volumes are going to be consistent if we have the same number of moles, even if they are different gases. Okay, so there's this thing that is important with gas laws, and it's called molar volume. The amount of space 1 mole of any gas occupies at standard temperature pressure. So any gas, if you have 1 mole and at standard temperature or pressure, it will take up 22.4 liters. When we put all of those things together, we get the ideal gas law. So we have Boyle's law, Charles's law, Avogadro's law, pressure and volume divided by the number of moles, and also divided by time equals R, which is a constant, and it's the universal gas constant. We put it all together. P1V1 over N1T1 is equal to P2V2 over N2T2, or PV equals nRT, where R is your gas constant. And that is what we're going to tackle in our next video. I will see you then. Bye.